Bismillahirrahmanirrahim. Welcome to our first course in the chemical engineering program. It is the fundamental chemical engineering calculations. It is the basic course and it's the core course for all other courses. You have to learn this course 100% because 100% sure you are going to use some of what you have learned in this course in the other courses. The reference for this course will be the book Basic Principle and Calculation in Chemical Engineering. It will be the 8 editions. So try to get the book because we are going to solve many exercises and questions from that book, and we will extract the information from that book. This course is divided into 2 chapters. The first one is material balance and the other one will be energy balance. We will talk about it later. The first chapter is divided to 4 sections. First section is basic concept and definitions. The second section is material balance without chemical reaction. The third one is material balance including chemical reaction, and the fourth section will be about multiple system material balance. So let's start with the first section, the basic definition. So what is a material balance? Material balance is the act of accounting and analyzing the materials within a specific system. What is a system? A system is the process you want to analyze. And what is a process? A process is an action or a series of action or operation that result in an end. For the system classification, we classify the system based on the boundaries. It's either open system or a closed system. Open system means materials can enter and leave of the system. Closed system means materials do not either leave or enter the system. So let's take a cup of tea as an example. Let's say you have made a hot cup of tea and you want to know you want to know when the temperature of the tea is getting cold. So the system, the materials we are analyzing is the tea itself. The system will be the cup, and the process that is happening is the tea itself getting cold because the surrounding temperature is less than the tea temperature, so the temperature is getting cold. Is the system open or closed? Because some water leave from the boundary. This is the boundary of the system. The cup itself, we have said the system. So because some water is evaporating due to the hot temperature, it's considered an open system. However, if we put a lid on it, the system will be closed. So no materials are entering or leaving. However, there is an operation happening. The temperature is still getting out as a form of energy, but we will talk about it later. But as of the materials, there is no materials entering or leaving, so it's a closed system. The operation is still happening. The temperature of the tea is getting cold, but there is no material entering or leaving, so it's a closed system. So another basic definition we want to classify is the process operations. We have 2 types of process operation. It is either a steady state or transient. So for the steady state means that the system variables such as flow rate, volume, temperature, pressure, composition, etc. does not change with time. On the other hand, for the unsteady state or transient, mostly we say unsteady state, but some people say transient. The system variables change as time change. So let's have an example to illustrate what I mean by steady state and unsteady state. So in this example, we have two containers containing 1 kilogram of 1000 kilogram of water. 1000 kilogram of water. In the first example, which is the steady state, the flow rate entering is 100 kilogram, and the flow rate leaving is 100 kilogram. On the other system, we have 60 kilogram entering and 100 kilogram leaving. The flow rate is still the same. So the 60 kilogram leaving of water, entering of water, and 100 kilogram of water leaving, it is the same with the time. However, what will happen after 5 minutes? We can say after 5 minutes, the amount of water, in the first example, the amount of water entered and the amount of water left is still the same as it was before 5 minutes. However, the amount of water that is in the containers is still the same. So that's what steady state means. There is no any change either in the system or the flow rate, temperature, composition, it's all the same. However, in the second example, the flow rate is still the same. That's a sign of a steady state behavior. However, if we look in the container, we can say there is a consumption of the amount of water that's happened. So that's what a transient process mean, or any steady state process. It could be different. Also, the temperature, if there is a change in temperature or pressure or composition, let's say concentration, if there is any change in this thing, it will be unsteady state. It has to be the same with time, like after 5 minutes, after 1 minute, after a certain amount of time. If there is any change, it will be unsteady state. Hopefully this example illustrates to you the steady state and unsteady state. So also we can see that if the system is a steady state, there is no accumulation or consumption in the system with time. This is one very important and crucial idea to memorize. So another concept is the process classification. We can classify the process based on 3 classification. The first one is a batch system. Batch means the process is closed. There is no materials enter or leave when you start the operation. A good example will be the blender. When let's say you want to make a smoothie, you put all the milk and smoothie ingredients, and you close the lid. Then you start the operation. After you start the operation, there is no material leaving or entering, and the mixing will happen. So when the operation started, the material did not leave or enter. That's a batch process. Another one will be the continuous, which mean materials enter and add, materials enter and leave the system when the operation start. We will have a faucet as an example. You open the valve, the water enter and leave. It will continuously enter and leave until you close the valve, which is stop the operation. For the last type of process classification is the semi-batch, which mean the materials either enter or lost, one at a time. So it cannot be enter and lost at the same time. And if that happen, it will be a continuous. A good example will say when you cook something, let's say you wanna cook a noodle or whatever. The system is the pot itself, and when you ignite fire, some of the water will evaporate. It will get out of the boundary of the system, and there is no during the operation, there is no adding of any ingredient, so it will be a semi-batch. So let's have an example to illustrate Material balance. How do we perform them, and how do we classify the system types, and etc. So the example says that a guy named Joe opens a new bank and deposits $1,000. After 1 day, the bank draw $300 from his amount and invest it, then return it as $350. In the end of the month, Joe gets his income, which is a total of $2,500, and then Joe pays the bills he has, which is $400 for bills, the sum of the bills he pay, also $1,200 for the rent of the house he live in. So what is the balancing material we are trying to balance? Basically, it's clear that is money, and the specific currency it will be either dollar or wherever he live. What is the system? The system is a clearly open system. The system, it will be the bank of the bank account for Joe, because we are trying to study how much money does Joe have. What is the system type? It will be open system, because money come and leave from the amount from Joe bank. What is the process classification? It will be continuous process, because it will be continuous process, because the money come and leave at a continuous rate. What is the process operation? It's either a steady state or unsteady state, because it's not certain if Joe always get the money at the same time, always pay his bills at the same time or not. It depends on that, so it's uncertain. For the last question, how much money does Joe has left in the bank? So let's start. Let's try and solve this last question. So this is the answer for the first 3 questions. As I said, the materials money is the material balance is money. The system is Joe bank account, open system, and the continuous process. Also, we have said the process operation is uncertain unless we get more information. So for the last question, first I have drawn the system. As I said, this is the boundary. Always try to draw the system. And the system, as I said, is Joe bank account. We want to account and analyze how much Joe does have. So this is the system. He initially deposited 1,000. So the system initially has $1,000. And then the bank have drawn $300 to invest. After that, the bank returned it. The bank returned as $350. So, and we see the arrow in, arrow which is directed as in. The arrow that is directed as in is how much money he get from his income, and this is how much money he is consuming due to his bills and monthly allowance. So if we want to solve it, it will be like the money in the bank equals to the initial deposit, because it's a positive, plus the income, because it's coming to Joe account, minus the outcome, because it's getting out of the minus sign, because it's getting out of Joe account, minus the money invested, because the money the bank withdraw it from Joe, so it's in the minus, plus the money gained because it's given to Joe. So if we do the sum of it, it will be the money left will be $1,950. So from the equation above, we can generate a general material balance equation. This is one of the most crucial and important equation for chemical engineer in general, because you will use it almost in all subjects that are related in chemical engineer, but it will be in a high level, because as you move on in the chemical engineering courses, you will add the information you have learned. So you have to understand this equation 100% and use it all the time and practice on using it. The accumulation, which is the money left in the bank or whatever is in the system, equals to the input minus the output plus the generations that are happened in the system, which is like how much money Joe got from the bank, minus the consumption which also happened in the system. In this example, it will be the investment that happened in the system without Joe involvement. This generation and consumption terms, we use it to state if there is a chemical reaction happening in the system. So it's one of the important things to understand. If there is no chemical reaction, mostly there will be no generation or consumption. And as I said before, if the system is steady state, the accumulation also will be zero, because in a steady state system there is no accumulation. So if the system is a steady state and without reaction happening, the input will equals the output. So let's move on. For us chemical engineer, in the material balance, we always follow the law of conservation of mass. The law of conservation of mass states that mass is neither created nor destroyed in a chemical reaction or physical transformation. To put it in a simple word, the mass of an element entered any system must equals to the mass out of the system plus the accumulation. If the system is steady state, there is no accumulation, so the mass in must equal the mass out. So let's have an example to illustrate. Let's say you have 100 kilogram of a mixture containing 10% NOH, 30% mercury, and 60% water. You want to extract the NOH from the solution of mercury and water. After you extract it, you have 90% of NOH and 10% of water at a flow rate of 11.1 kilogram, and on the other flow rate you have the mercury and water. So let's apply the law of conservation of mass. So for the overall balance, we have 100 kilogram is being split into two streams. One of them is 11.1 kilogram and the other is 88.9 kilogram. So we can see that the 100 is equals to the 11.1 kilogram plus the 88.9 kilogram. So this is valid express, because we said mass is neither created nor destroyed, and in this system there is no accumulation, so the mass in must equals out. So because there is no accumulation in the system, we can see that there is no mass here. Also there is no chemical reaction happening, so there is no generation or consumption happening. So let's now try to analyze what is happening in the NOH. So if we apply the law of conservation of mass to the NOH, we can see that the amount of NOH is entering is 10% of the 100. So if you want to get how much NOH is entering, you multiply the percent composition times the stream flow rate. So if and then in this stream we don't have any NOH, so it will be 0 multiply with the stream value, and in this stream we have 11 kilogram multiplied with 90 kilogram. Let's check if this is valid equation or not. It will be 10 kilogram of NOH entering equals to 10 kilogram of NOH leaving. So this process is also constantly with the law of conservation of mass. So if we do the same for the mercury balance, it will be also 30 gram of mercury entering and 30 gram of mercury leaving. And we can also do the same for the water balance. It will be in this I have put it as 59.7 kilogram of water, because I wanna tell you that in actual real life processes there is always some of the material lost in the pipes and in the reactors and in the chemical column and equipment. So sometimes it's good to neglect the small values and put the approximately, because it will not affect the process. So in real life there is some materials are lost, but we do not put it as accumulated in the system because it's a small amount and we usually neglect it. So let's move on to one of the most crucial concept, which is the degree of freedom and basis and the scale factor. Degree of freedom is the analysis of a system variables and if it could be solved or not. So you use the degree of freedom before you start solving any system to understand, is this system solvable or not. The equation of degree of freedom is very simple. The number of unknown variable minus the number of independent equation. So let's move back to our system. In this system we have 4 equations. We have the overall, and we have the NOH mass balance, the mercury mass balance, and the hydrogen mass balance. However, you can realize that the sum of these 3 is equals to the 100 kilogram. So it will be redundant to write this system as 4 material balance, because the sum of these 3 is equal to 100 kilogram. So we usually, when we have 3 components, we say if we have 3 components, we say we have 3 material balance. We do not write the overall as a independent equation because it's redundant and it is the sum of it. You can use, if you want, if it's easier to solve using the overall mass balance, you can neglect one of the component balance and use the overall, but you cannot use all of them. You have to set to have the number of a component is always equals to number of independent equation. So also independent equation sometimes is a equation that you have learned in general chemistry or physics. It doesn't have always to be the number of component. because it depends on the question. Sometimes the question gives you the density and you can get the flow rate from the density, and the volume you can get it from the density, and the mass also you can get it from the density. So this is the, if you get the density of any component, it's consider one independent equation that you can put in the system. As we move on and solve examples, you will understand what I mean. So let's move on. After you solve the degree of freedom equation, you have three output that is possible. It's either 0, minus, less than 1, or higher than 1. If it is 0, which is the ideal and what we want, the system is solvable and one unique solution exists. So you always want the degree of freedom to be 0. If it is bigger than 1, the system is not idle and you have to get more specification to solve it. If it is less than 1, the system is solvable, you can solve it, but you have to be careful that there is no contradiction happening with your values, and you can solve it. But it's always better to have the degree of freedom equal to 0 to solve the system without any other possible solutions. So let's have an example and try to find out the degree of freedom for this example. We have 100 kilogram of water entering the mixing process for a cake batter, and we have unknown flow rates of a mixture of 10% sugar, 30% chocolate powder, 60% flour. It's entering a mixing process to make the cake batter. The product stream rate, we do not know how much is leaving, and also we do not know the compositions of the mixture in the product. So if we analyze the system, how much unknown do we have? We don't know what is the flow rate entering of the mixture, and we do not the product flow rate. We do not know the composition of the materials leaving. As you see in the flour, I did not put X4. Even though we do not know how much composition of a flour, but we know from the general chemistry that the composition of any mixture is equals to 1. So the sum of composition is equals to 1 in any mixture. We know that from general chemistry. So we can get 4 by, if 4 is equal to 1, x4 is equals to 1 minus x1 minus x2 minus x3. So we can get it, we can get x4, and we don't have to put it as an unknown. So if we do the degree of freedom, as I said, we have 1, which is F, the stream entering. We have 2 unknown, 3 unknown, 4 unknown, and 5 unknown. So the number of unknown entering is 5. The material balance, we have water, sugar, chocolate powder, and flour. That's a 4 material balance. We can see that the degree of freedom is bigger than 1, as we said, if it's more than 1, it's not solvable. So what will you do if you have a system like that? With 1 missing variables. Here I want to introduce the concept of basis. Basis is an assumed variable to help you solve the equations for any specific system you have. a good tip is always to try and use a basis that is the easiest to solve. Do not pick a basis that will make the question hard to solve or impossible to solve. So in this example, for instance, if we take F or B as a basis, it will be easier to solve. However, if we take any of the composition, it will be hard because we don't know the value of B also, and we can't get the composition value. So the basis we have taken is I have taken F as a basis of 50 kilogram of cake mixture, and if we apply the total material balance, we can get the value of B. And if we do with the component balance of water, sugar, and the chocolate powder, and we can get the value at the compositions of for the mixtures. And as you can see, X4 you can either solve it by the same way, or you can use the equation we have said, the sum of X, the sum of composition is equals to 1. You can solve it either way and you will get the same value as you have said, is 0.2 and 0.2. So let's say after you have taken a basis and solved the system, we have taken a basis and solved the system, we have found all the compositions. Let's say you want to change, like let's say the density of the cake powder was not let's say the density of the cake powder after you've combined the 100 kilogram of water with 50 kilogram of water. Let's say the density was very liquidy and you want it to be more stiff, and you want to change the density of the product, and you want the density to be 180 kilogram for each cubic meter. So let's say you know the volume of the reactor and it's equal to 1 cubic meter. The volume of the mixer at the mixing is 1 cubic meter. So we know that density, the mass is equals to density of times the volume. So after that we have taken the volume to be 180 kilogram of mixture. So this 150 kilogram you want to change it to 180 kilogram. Here I want to introduce to you another very crucial concept, which is scale factor. Scale factor, it's the ratio of actual value over the basis value. We always use it in an engineering calculation. We do the calculation with a basis value that is easy to solve for our system. Then we find out the actual value we want and get a scale factor. The scale factor for this process, for example, the actual value that we have said we want the cake to be, the product to be, is 180 kilogram. This is our actual value, and the basis which we use to solve the system is 158 kilogram. So when we get the scale factor, to transform this process to the actual process we want, we use the scale factor value we have find here. We multiply it with all the variable with the new streams that we want. So yeah, as you can see, we multiplied the flow rate 50 with the scale factor we have, which is 1.2, and we have got the new value. And here we have multiplied the 90 kilogram with 1.2. I mean, it was one. This is a mistake. It's 150 kilogram with 1.2. This is 150 kilogram with 1.2, and we will get 80 kilogram. and you do not change the streams, because the streams do not change. Only you do not change the composition. The composition will stay the same, just the value of stream entering. Scale factor in this example, you can say if I do the calculation again, it will be easy. However, if you have more than one stream, you have like 50 or 60 streams entering, scale factor will be easy way to solve the example. You pick a nice and simple basis to solve the system. After that, you use the scale factor to transform from the basis value to the actual process value. So that was the end of the lecture. Let's recap what we have studied. The general material balance, we have said accumulation is equals to input minus output minus consumption plus generation. If we have a steady state system, there is no accumulation, so the term accumulation will be 0. So the input minus output minus consumption plus generation is equal 0. If we have no chemical reaction, consumption and generation will be 0. However, we will study it in this chapter. So it's good to leave it as that. The input minus output minus consumption plus generation equals to 0. All the process in chemical reaction, chemical engineering mostly are steady state, but sometimes we have unsteady state. So it's good to know this question. System boundaries, we said it's either open or closed. The process classification, continuous, batch or semi-batch. Process operation, steady state or transient. The basis is an assumed variable to carry out the calculation. Degree of freedom, we said the unknown of variable minus the independent equation. The degree of freedom is always good to have it 0 to have one unique solution for the system. And the scale factor is the actual value over the assumed value or the basis. It's either assumed or basis. So here is some question. I will try to solve it by yourself, and I will upload another video solving this equation. Try to stop the screen and solve it. And here is another list of questions. So that was the end of the lecture. I will upload, hopefully short, I will upload another video for solving the question. Before you watch the other video, try to solve it by yourself, because you learn better when you solve it by yourself, and you learn when you make mistakes. So that was it. See you soon, hopefully.